Hello friends, in this video we are going to study about the root locus technique. The root locus technique is an important tool in the analysis and design of control system. This technique was developed by W.R. Evans. So what is the root locus technique? The root locus technique is the plot of the locus of the roots of the characteristic equation. Okay, so let's see what is the definition of this root locus technique. The root locus diagram is the plot of locus of roots and roots are what? They are also known as the closed loop poles of the system. So roots, which are also called So root locus diagram, it is the plot of locus of roots, and roots are also known as the closed loop poles of the system, and these roots are the roots of the characteristic equation. Characteristic equation of a control system, we know that it is given by 1 plus GSHS equals to 0. So when we calculate the roots of this characteristic equation and then plot the locus of these roots with respect to gain k, then that plot is known as the root locus diagram. Okay, so what we are doing, basically we are plotting the roots of the characteristic equation. Here we have used the term this locus. So locus is what? Locus, it is a curve or figure of some points which are satisfying certain equation. Okay, so here the equation is the characteristic equation and the points are the roots. So what we are plotting? We are plotting the locus, or we are plotting a curve, and that curve is joining some points. These points are the roots of the characteristic equation, such that this curve which we are drawing, it is satisfying the characteristic equation. And what we are plotting the roots with respect to the gain k of the system. So it is the basically the definition of the root locus diagram. Okay, now this method, as you know that this method, it gives us some indication, or it gives some information about the absolute stability and the relative stability of the system. So as we have said that root locus technique is an important tool in the analysis and design of control system. So analysis can be done because root locus diagram gives us information about the absolute and relative stability of the system, and designing of the system can be done because here we are plotting the roots with respect to gain k. So if we adjust the value of this gain k, then it is a type of designing of a system. So we are doing both the analysis and design of the control systems using this root locus technique. So let's see how we are doing it. Root locus technique. gives an idea So as the root locus technique, it is giving us information about the absolute stability and to some extent about the relative stability. So it can be used in the analysis of a control system. And how designing this gain K So this gain K can be adjusted according to the desired location of the closed loop poles. So designing means we are adjusting this gain K. So this root locus technique also helps in the designing of the control system. So whenever someone asks you about what is a root locus technique, then root locus technique, it is the plot of locus of roots of the characteristic equation with respect to the gain K, and it gives us information about the absolute stability and relative stability, and also it helps in the designing of a control system because we can adjust the gain K according to the desired location of the poles. Okay, now let us see the angle and the magnitude conditions of this root locus technique. So let us see what are these conditions which help us to plot the root locus. Now consider a system having the block diagram. It is the input, so this is a feedback control system. In the feedback path, we are having the gain as Hs, and this is the forward path gain Gs. Rs is the input and Cs is the output. So if we write the transfer function for this system, the closed loop transfer function, then it will be So the transfer function, it is the ratio of the Laplace transform of the output and the Laplace transform of the input. So transfer function, that is Ts, it will be Cs by Rs, and if we write it, it will be Gs upon 1 plus Gs Hs. So it is the closed loop transfer function of this system. Now if we write the characteristic equation for this system, the characteristic equation, it can be obtained by equating this denominator part, that is 1 plus GSHS equals to 0. So the characteristic equation for this system is So the denominator part of this system, of this transfer function, is 1 plus GSHS. And if we equate it to 0, it will become the characteristic equation of the system. Okay. Now if we bring this one to the right hand side, it will be GSHS equals to minus 1. Now this G and H, as they are in S domain, so as the S plane is complex, complex means that S is equals to sigma plus J0. Okay, so here we can write the above equation as this GSHS will be equals to minus 1 because it is the real part and there is no imaginary part, so we will have J0. Okay, so here we were having sigma plus J omega, and omega here it is 0, so we can write GSHS as this. Now this, in this GSHS, if we take the magnitude of this, then it will be magnitude of GSHS, it will be 1. Okay, because GSHS was equals to minus 1 plus J0. J0, it is the imaginary part, taking only the real part and taking the magnitude, that is absolute value, so it will be 1. Okay, now this condition, that the magnitude of GSHS, it is equals to 1, it is known as the magnitude condition to plot the root locus. So whenever we want to plot the root locus of a system, then this condition, that the magnitude of GSHS should be equals to 1, it should be satisfied. Okay. Now let's see what is the angle condition to plot the root locus. Now angle condition, it is given by the equation for the angle condition is the angle of this GSHS, it should be plus minus 180 degrees to m plus 1, where m is from 0, 1, 2 till its last value. Okay, so the angle of this GSHS, it should be plus minus 180 degree to m plus 1, where m can be 0, 1, 2 till infinity. So this is the angle condition to plot the root locus of a system. So we can say that as we have derived this GSHS from the closed loop transfer function of the system, so we can say that the root locus of a system can be plotted, or it is plotted using the closed loop transfer function of the system. So the root locus of a control system is determined from the closed loop transfer function of the system. And also when we are constructing the root locus, as we we have studied that there are two conditions, angle condition and magnitude conditions, and these two conditions must be satisfied to plot the root locus. So when we are constructing the root locus in the S-plane, the angle condition is used to find the points on the root locus. And the magnitude conditions is used to find the values of k on the root locus. Okay, so what we are doing, we are using the closed loop transfer function of the system to plot the root locus, and from that closed loop transfer function we are deriving the angle condition and the magnitude conditions, and we will use the angle condition to find the points on the root locus, and we will use the magnitude condition to find the values of k on the root locus. Now there is a point which you have to keep in mind, that while you are using the angle condition, so as we have said that the angle condition, it is used to find the points on the root locus of the system. So we can use this angle condition to check that whether a point it is existing on the root locus of the system or not. When that point is satisfying the angle condition, that means that it is lying on the root locus of the system. And using the magnitude condition, we can calculate the value of k for that system. So using the magnitude condition, value of k can be calculated at the above point. So what we are doing, we are checking a point, that whether this point it exists on the root locus or not. If it exists on the root locus and satisfying the angle condition, then we can calculate the value of k at that point using the magnitude condition. Let's take an example, that suppose we are having a point s equals to -1. So if this point is satisfying the angle condition, that means that for a system it is lying on the root locus of that system. And if it is lying on the root locus satisfying the angle condition, then at this point s equals to -1, we can calculate the value of k. K is what? Gain of the system. So this is the use of the angle and the magnitude conditions while plotting the root locus of a system. Let's take an example so that you can clearly understand this. Consider a simple control system whose open loop transfer function is we are given the transfer function, open loop transfer function, that is GSHS equals to K upon S plus 3. Okay. Now we know that root locus can be plotted using the closed loop transfer function of the system. Here we are given the open loop transfer function. So let us determine the characteristic equation of the system. Okay. Closed loop transfer function will be Ts equals to 1 Gs upon 1 plus GSHS, and from here we can get the characteristic equation by equating this denominator part to 0, that is 1 plus GSHS equals to 0. This is the characteristic equation. So let us obtain the characteristic equation for this system. It will be putting the value here, 1 plus GSHS is what? K upon S plus 3 equals to 0. Solve it, we will get S plus 3 plus K upon S plus 3 equals to 0. Now if we shift this S plus 3 to the right hand side, it will become 0 and we will be left with S plus 3 plus K equals to 0. Let's obtain the value of S. It will be minus K minus 3, because if we shift this 3 plus K to the right hand side, the sign will get changed. So it will be S equals to minus 3 minus K, or we can write it in the way that minus K plus 3. So this is the root of this characteristic equation. Root, because we are getting the value of S from that characteristic equation, so it will be known as the root of the characteristic equation. The root of the characteristic equation is also known as the pole of the, or we can say the closed loop pole of the system. So this S equals to minus K plus 3 is also the pole or the closed loop pole of the system. So poles and root, they are one and the same thing. Now let's calculate the value of S for various values of K. Okay. Now for various values of K, K should be positive because it is gain of the system. So gain is always positive. So K should be positive. So the root is, we will take different values of K and then we will see that what will be the value of this root. Okay. So let's take a form a table. Let's take different values of K. Suppose we are taking 0, 1, 2, 3 and infinity. Now put this value in this equation and let's see what will be the value of the root. If we put K equals to 0, then it will be minus 3. If we put K equals to 1, then 1 plus 3 is 4, then minus 4. If we put here 2, then 3 plus 2, 5, then minus 5. If we put here 3, then 3 plus 3, 6, then minus 6. And if we put here infinity, then it will be minus infinity. Okay. So as the value of K is changing, we are also getting different values of the root. Now let's plot these values of this root in the S plane. The root is the root determined above, that is the different values of S which we have obtained in this table, is this plotted in the S plane. Because we have said that the root locus is what? It is the plot of the locus of the roots of the characteristic equation. We have obtain the various values of the root of the characteristic equation. Now we are going to plot this root on the S-plane. How we can plot this? Let's see. S-plane, it consists of the imaginary and the real axis. It is j omega and it is sigma. Why? Because S is equals to sigma plus j omega. So it is the sigma, that is the real axis, and it is j omega, that is the imaginary axis. This is positive and this is negative. This is positive, it is negative, and this is S equals to 0. Now we are having the values as, let's see the table again. We are having for k equals to 0, S is equals to minus 3. So we will plot this pole here. Because it is a root, root is also known as pole, and we know that whenever we plot the pole on the S plane, then we plot it with the help of a cross. Okay, we denote it by a cross. Cross is used to denote the pole on the S plane. So here we are having S equals to minus 3. Okay, minus 1, minus 2, minus 3, minus 4. So let's have this minus 1, minus 2, minus 3, minus 4, minus 5, and here we are having minus 6. Okay, we are having a rough approximations here. So S equals to minus 3 for k equals to 0. So here we are having S equals to minus 3. So we will plot it by a cross. Okay. Now for S equals to minus 4, k equals to 1, we were having S equals to minus 4. So again S equals to minus 4 is another root value. For k equals to 2, we were having S equals to minus 5. For k equals to 3, S equals to minus 6, and k equals to infinity, S is equals to minus infinity. So S equals to minus 5 is also a pole, S equals to minus 6 is also pole, and then minus infinity in this side. So what we are having? We are having 4 poles. Minus 3 is for k equals to 0, k equals to 1, k equals to 2, and S equals to minus 3 is for k equals to minus 3. And then we are having k equals to infinity, then S is equals to minus infinity. So our root locus, it will be from here to in this direction. Okay, it will go in this direction, that is for minus infinity. So what we have done, we have plotted the locus of the roots. Locus means we are joining these points. So we are joining all the points, we are getting a straight line, and this is the locus of the roots of the characteristic equation. So this diagram will be the root locus diagram for this system. So I hope this video is clear to you, this topic, that what is a root locus technique and what are the angle and the magnitude conditions of the system. I hope this is clear to you. Thank you.